This is 4.2.2 Young's modulus of elasticity. Now, last time we talked about spring constant, and I said spring constant depends on the shape and size and material of that particular spring. Spring constant is not a material property. It depends on the geometry of the thing that you have. Young's modulus, however, is a bulk property, so it's a material property. So it doesn't matter what shape and size of copper I have, everything that's copper has the same Young's modulus. Everything that's aluminium has the same Young's modulus. Everything that's iron has the same Young's modulus. So Young's modulus is a material property. And Young's modulus tells you how difficult or easy it is to stretch or compress a material. So, for example, the Young's modulus of steel is larger than the Young's modulus of copper because it's easier to stretch copper. Now, Young's modulus is related to two other quantities, stress and strain, which we'll go over now. So stress is something that a material experiences when there is a force acting on that material. And stress is simply just the ratio between the force and the cross-sectional area of that material. And the symbol for that is the lowercase sigma. So, say we've got some material with a circular cross-section, and we apply a force on it. This area here is the cross-sectional area. A. And stress is equal to F over A. So sigma is stress, and it's measured in pascals. F is force, measured in newtons. And A is area, or cross-sectional area, measured in meters squared. Strain is simply just the ratio between the extension and the length of a material. Or we could write it as E over L. So both E and X stand for extension. Now, because it's extension over length, the units for extension are in meters, the units for length are in meters. So meters divided by meters means that stress has no units. Oh, sorry, that should be strain. Let's change that. It's a typo. Strain. There we go. So strain has no units. Right, next. Types of cross sections. So the most typical type of a cross section is going to be circular, but you can also have rectangular or square cross sections as well. The important thing is that you recognize in the question what type of cross section has been given to you and calculate its cross sectional area appropriately. So we could have circular, or we could have rectangular. So if it's circular, you'll be given either the radius or the diameter, and you know that the area is going to be pi r squared. For the rectangular, you'd need to know two sides, or one side if it's a square, and the area is just equal to a times b. So once you've got all of that information, then you can work out the Young's modulus. So Young's modulus is just stress over strain. And then, so you've got stress, which has units pascals, divided by strain, which doesn't have units. So the units for Young's modulus is just pascals. Now a question that might arise here is, so if it doesn't have units, then technically isn't that like dividing by 0? And the answer is no, because when something doesn't have units, you treat it as if it's 1. Right? Because a unit is a factor that you multiply to that magnitude. Yeah. So when you have 2 meters, it's 2 times this quantity we call a meter. When you have 2 volts, it's 2 times this thing we call a volt. So when you have no units, because it's a unit divided by unit, something divided by itself is 1. Yeah? Now, the reason why I gave you a second version of strain, where I used E instead of X, is because it makes the next equation easier to remember. So another way to remember the equation for Young's modulus is to substitute the equations for stress and strain into it, and then we'll get another equation. So sub in stress is equal to F over A, and strain is equal to E over L. If we do that, we get E is equal to F over A. And if we put E over L, because it's been divided, flip it over and multiply it. So the L goes on top, the E goes on the bottom. E equals to flee. And that's an easy way to remember it. Start a new page. So next we're going to look at measuring Young's modulus. Now, for practical purposes, when we do it in a lab, we will do it horizontally rather than vertically and use pulleys to transfer vertical force into a horizontal force to stretch a wire. And we'll use very, very long wires so that we can yield in large extensions for small amount of weights added. But technically you could do it with a short wire as well, and you could do it vertically. You just need to add lots and lots of mass to actually see its effects. But I'll show you both ways. In either case, you need an anchor point where the wire is attached that doesn't move. And you need some way of measuring the length and extension of the wire. You then load it with mass. So this is example 1. And example 2 would be to have it like that. So that's our wire, that's our mass, there's a pulley here, that's our wire again. The length of the wire is measured from the top to the bottom. In this case, the length of the wire is the sum of that length, or I should do it like this actually. This would make it better. So it's the entire length of the wire from there to there. And call that the length. So in either case, you first need to measure the diameter using micrometer, and you do it several times over the length of the wire and take an average. Okay, that's glitched. Let's fix that. So several times over length of wire and take average. Then you're going to measure the length of the wire using, now depending on the length of your wire, if your wire is short enough you could use a meter ruler. If your wire is very, very long, then you have to use something else like a tape measure. Or you could also use a vernier scale if you're measuring extension. So measure length of wire using meter rule or tape measure. You also need to know what masses you're using. So you use a balance to measure your masses. Just because it's printed on it 100 grams doesn't mean it's actually 100 grams. So measure mass using balance. Then for a series of values, of applied force, which comes from F equals to mg, you're going to measure the extension. Then you're going to calculate stress and strain. And then you plot a graph of stress against strain. And if you did this for many, many values, you'll get a straight line, which then curves, dips, goes back up, and looks something like that. That initial straight line is called the Hooke's law region. So in that region, it obeyed Hooke's law. The gradient of the Hooke's law region will give you the Young's modulus. Next page. Next, we're going to look at the stress-strain graph. So we'll just sketch the same graph again. And we'll label some points. So that the point at which it just about stops being a straight line, we'll label that A. A short distance after that where it's properly curved is B. Then the top of that first peak is C. The top of this final peak, we'll call that U, and the final bit there, we'll call that D. That initial straight line bit, the Hooke's law region, is elastic behaviour. Where the stretched wire or spring or any material will return back to its original shape without permanent deformation. Then A is the limit of proportionality. This is where the graph stops being a straight line. B is the elastic limit. At this limit and past it, the wire will be left with permanent deformation. C is called the yield point. Now, if you ever see the yield point happening in real life, it looks quite freaky. So up to that point, you've been loading masses slowly, and each time you load a mass, you see the same extension each and every time. Yeah? So for example, if I put 10 newtons and I saw 2 centimeter extension, when I add another 10 newtons, I see a further 2 centimeter extension. Now, after the yield point, you add another 10 newtons, and suddenly, instead of getting 2 centimeters of extension, you suddenly start getting 10 centimeters, 15 centimeters. So the wire just suddenly starts stretching a lot for very little additional force that you load onto it. So this is called the yield point. So the yield point, wire stretches a lot or large extensions for small forces. Or you could say large strain for little stress. At that point, the yield point, the wire has now weakened. Past the yield point, we now have something called plastic flow. So the material now behaves like a plastic, and all deformations are permanent. Then U is called the ultimate tensile stress. Which is the largest stress that the material can take. And D is called the breaking point. All right, start a new page. Stress strain definitions. So we're going to do yet another stress strain graph. But we're going to draw 3 different ones. So we're going to label this top one as steel, this one as glass, and this one as copper. And we're going to define the following words: stiff, brittle, ductile, tough, and strong. So stiff just means that it has a large Young's modulus. The Young's modulus is also related to the spring constant, which is sometimes called the stiffness constant. So stiff means large gradient, which is the Young's modulus, which is difficult to stretch. Brittle means that it breaks very soon after the elastic limit. Ductile means that you get large strains for small stresses. things that are ductile tend to be easy to shape. So for example, if you want to roll them into wires, you want a material that's ductile. Then tough means that you need a lot of energy to stretch it. Which also means that it stores a lot of energy when it's stressed. And this is related to the area under the graph. And then strong means that it has a high UTS, ultimate tensile stress. So let's go through these and say what they are. So stiff has a large gradient and is difficult to stretch. If we compare the three that we've drawn on this graph, steel has the largest gradient. So steel is stiff. Next, brittle means that it breaks soon after the elastic limit. The only one that breaks very soon after the elastic limit is glass. So glass is brittle. Ductile, big strain for little stress. Copper, again, it's got very small stresses but very large strains. So copper is ductile. Then tough needs a lot of energy to stretch, which is the area under the graph. The one with the largest area under the graph is steel. So steel is also tough. And then last one, it's strong, has a high UTS. Steel has the highest UTS. So steel is also strong. And that's the end of 4.2.2.